All right, thank you all so much for watching the first part of this two-part video about showing Khovanov homology detects the torus link T26. In this video, we'll give an overview of Khovanov homology and link detection more generally before giving a sketch of a proof that Khovanov homology detects this torus link T26. And for more details about the proof that Khovanov homology detects this link, you can see the second part of this two-part talk where more of the details are given. So before I start talking about any of the math, I think I just want to take a minute to acknowledge that I'm recording this talk on the stolen territory of the Massachusetts people. And I think it's important to take the time to say this as part of reflecting on a continuing history of colonialism and genocide here in the United States. So today I'll be talking about Khovanov homology of links. So just as a brief background, Khovanov homology is an invariant of a link defined by Khovanov. So it's some categorification of the Jones polynomial. And what that means is given a link L, you get some bigraded abelian group Khovanov homology called the Khovanov homology of L. And if you take a graded Euler characteristic of the Khovanov homology, you get the Jones polynomial of L. And finally, this is an invariant that's combinatorially defined. So what that means is given a diagram for your link L, there's some simple rules you could follow to construct a chain complex from the diagram. And if you take the homology of this chain complex, you'd get the Khovanov homology of your link L. And I should say, because of this combinatorial definition, computers can compute Khovanov homology relatively quickly because they just follow these simple rules to compute this chain complex. So given this combinatorially defined invariant, as a low-dimensional topologist, what I think would be a very natural question is, well, if I'm told that the Khovanov homology of some link L looks like this, what do I know about my link L? Are there topological statements that I can make? And this, I think, is a very natural question because an analog of Khovanov homology would be not Fuller homology. That's categorifying the Alexander polynomial. And in the world of not Fuller homology, there are many topological statements you can make about knots and links from knowing they're not Fuller homologies. So it's natural to ask, what about in the setting of Khovanov homology? And trying to answer this question is really getting at what sort of topological information is contained in the Khovanov homology of a link. So an example of this type of question would be, say I fix a specific simple link L0. So then if I knew that the Khovanov homology of L is isomorphic to the Khovanov homology of L0, would I actually know that my link L really is the link L0, is isotopic to it? So if this is true, then we'd say that Khovanov homology detects the link L0. And let me just point out, if you know that Khovanov homology detects a link L0, it gives you a very quick way of recognizing if a diagram of a link is really a diagram of L0, because you can ask your computer to compute the Khovanov homology of the link in that diagram and see if it agrees with the Khovanov homology of L0. And because you know Khovanov homology detects L0, this will give you an answer of if the link in your diagram is the link L0. So with this setup of knowing that we want to ask about when does Khovanov homology detect some specific link L0, we might want to know, well, what links are known to be detected by Khovanov homology? And so the first result in this direction was due to Kronheimer and Refka, where they showed that the unknot is detected by Khovanov homology. And I think every other result since then is in some way building on this, because if Khovanov homology didn't detect the unknot, you wouldn't be able to show Khovanov homology detects these other links either. So after that, it was shown Khovanov homology detects the unlink, so disjoint unions of unknots. This was due to Hedden and Nee and Batson and Seed, building on the Hedden and Nee's earlier work. And this same result has actually been extended to show that Khovanov homology detects split links in general. So this would be a special case where Khovanov homology detects the unknot and detects disjoint unions of the unknot. Since this work, Baldwin and Sivak have shown that Khovanov homology detects the trefoil. This is, as of recording, the only other not known to be detected by Khovanov homology besides the unknot. And so the links we'll see will be built with components that are unknots and trefoils. So the first such link with Baldwin, Sivak, and G have shown that Khovanov homology detects the Hopf link. And since then, G and Zhang have shown Khovanov homology detects the torus link T24, and also that Khovanov homology detects the connect sum of two Hopf links. And recently I showed that Khovanov homology detects the torus link T26, which would be some extension of the results that Khovanov homology detects the Hopf link T22 and the torus link T24. And since this, there's been some other work showing Khovanov homology detects the link L6N1, the link L7N1, and the connected sum of a trefoil and a Hopf link. And so you'll notice that all these results are somehow building on the knot detection results that Khovanov homology detects the unknot and the trefoil. And there's some topological properties of some of these links that are common, which lets the same sorts of techniques be used to show detection results for all these links. And we'll actually see what some of those tools that you'd use to show a detection result are. So in particular, like I've said before, we'll sketch a proof that Khovanov homology detects T26 by the end of this talk. But before we do that, we'll give some overview of what tools you might use to prove a detection result. And after we've done that overview, we can see how to put a few of those tools together to prove that Khovanov homology detects T26. So I think that the tools that are used really come in more or less two different styles. So the first type of tool that's used is tools that are internal to like a Khovanov theory. So the first of these tools is what's called a link splitting spectral sequence. So this is a spectral sequence from a link, the Khovanov homology of a link L to the tensor product of the Khovanov homologies of the components of L. And this is also the same as the Khovanov homology of the split link built out of these components through disjoint unions. And so that's why it's called a link splitting spectral sequence. And so this can be used to identify when you have components of your links that are unknots or trefoils, because Khovanov homology detects these knots. And it can also be used to determine the linking number between components of your link. The other tool that's internal to Khovanov homology that is sometimes used is a spectral sequence to Lie homology. So Lie homology is some variant of Khovanov homology where the rank is always 2 to the number of components of your link. So given this spectral sequence, you can use it to identify the number of components in your link because that's recorded in the total rank of Lie homology. And the homological grading on Lie homology also records the linking number between your components. So this is like some extra data that you can see from Lie homology and the spectral sequence from Khovanov homology to Lie homology. But just knowing that components of your links are unknots or trefoils and knowing linking numbers between components isn't usually enough to prove a detection result. So you need some more information than this, and how people have gotten that information so far is through spectral sequences to a floor theory. And these spectral sequences and how they're used are really divided up in two ways, I think. So the first would be the Ajvar-Szabo spectral sequence to the Hagard floor homology of the branch double cover of a link. And so how this has been used is to detect splitting spheres in the complement of a link. And so this would be to show that Khovanov homology detects the unlink, or Khovanov homology detects split links more generally. And a splitting sphere in the complement of a link corresponds to S1 cross S2 summands in the branch double cover of your link. So this spectral sequence detects these splitting spheres by detecting S1 cross S2 summands in the branch double cover. The other type of spectral sequence is either the Kronheimer-Marufka spectral sequence to I sharp of L, which is some invariant of L defined using instanton floor homology, or the Dallin spectral sequence to not floor homology. And both of these are used in similar ways, so they're listed together. Both are used more or less to understand Seifert surfaces for knots. So this would be how you could detect the unknot, is by knowing that you have a Seifert surface that's a disk. And then also you can use these theories to understand how those Seifert surfaces interact with the rest of your link if you have more than one component of your link. So in particular, both link floor homology and some variant of I sharp can detect braid closures in the complement of an unknot. And this is something that we would use to show that Khovanov homology detects T26. So why don't we see how to put some of these tools together to show Khovanov homology detects T26, at least as a sketch of a proof. So we're going to show that if the Khovanov homology of a link L is isomorphic to the Khovanov homology of T26, then L is isotopic to T26. So we can start by assuming that their Khovanov homologies are the same. So then our first step would be we could show, using the spectral sequence to Lie homology, that L has two components, and that the linking number between these components is 3. So we've learned some information about L, but this isn't enough information to be sure that it's T26 and not some other link. So here's an example of a different link built out of a unknot and a trefoil where the linking number between these two components is 3. So we'd want to rule out some link like this. And so by using the link splitting spectral sequence, we could actually see that both components of L are unknots. So that would rule out the link that we just saw, where one of our components wasn't an unknot, but it would still leave a link like this, where we have two unknotted components, and the linking number between these unknotted components is 3. But this link still isn't T26. We want to find some more information about our link L from its Khovanov homology to rule out something like this. And so how we find that final bit of information is if we use the Dallin spectral sequence to not floor homology, and the fact that link floor homology detects braid closures in the complement of an unknot, we could see that one of our unknots is a braid in the complement of the other. So in that example we just saw, that wasn't a braid in the complement of the unknot. So we know that that's not the sort of thing we want to be thinking about. And instead, actually, we know it's a braid and the linking number with the axis is 3. So it's a 3 braid that represents the unknot. And so there's only these 3 different 3 braids up to conjugation that represent an unknot shown here. And so taking the closures of these braids with the braid axis gives us an exhaustive list of what links L could be from this topological information. So we know that if we had a link L whose Khovanov homology was isomorphic to T26, then L would have to be in this finite list of 3 links built out of braids and their braid axis. And so our final step would just be computing the Khovanov homologies of the different links in this family, in this finite list, and seeing that Khovanov homology detects T26 out of this list. So all of the links that aren't T26 in this list have different Khovanov homologies. So our link L that we started with, that has an isomorphic Khovanov homology to T26 and was in this list, has to be T26. So now we've shown that Khovanov homology detects the link T26. So thank you all so much for taking the time to watch this video. I hope you also watch the second part of this video where we go into more details about how to show Khovanov homology detects T26. And if you have any questions, please leave a comment so that I can try and answer your question. But thank you again. I hope you all have a great day.